I'm going to address this by first going through a bit of history of the hydrology and our estimates of the phosphorus loading to Lake Winnipeg. I'm going to try to achieve this by addressing these four questions. First of all, how have the flows of the major rivers going into Lake Winnipeg changed over the last century? How has that affected the load of phosphorus to the lake? What controls the flow of the water in the Red River, and you'll see why I'm focusing on the Red River as we get into this, and can we do anything about it? So this graph shows the flows in the three major rivers entering Lake Winnipeg. And those are the Winnipeg River, the Saskatchewan River, and the Red River. And also shown on this is the sum of those three lines, which is the total inflow from these three rivers, which is approximately equal to the outflow in the Nelson River. Most of the water that comes into Lake Winnipeg comes from these three rivers. And there are a few interesting things to see over the approximately 100 years of record that comes from Water Survey of Environment Canada. First of all, we notice that the Saskatchewan and Winnipeg rivers used to contribute about equal amounts of water to the lake if we go back to the beginning of the century. Now the Winnipeg River has increased somewhat in flow and the Saskatchewan River has dropped generally. And of course we see there's quite a bit of up and down in the long term. If we look at the flows of the Red River, there are a couple of things that are very interesting. One is that in the 30s, the Red River had very low flows, and you can see that the total flows into the lake were very low at that period of time as well, and we all know the stories about the dirty 30s. And the other major feature that we notice in the Red River is that in the last 15 years, the flows have been very high relative to the long-term history. This is important because if we look at the relationship between the concentration of phosphorus in the river water and the discharge, this is an example for the Red River. We've also done this for the other rivers. At least over the last 40 years, where we do have records of phosphorus concentrations, you can see that the concentration of phosphorus in the river actually rises somewhat as the flow increases. And if we take this relationship, or a line that represents this relationship of between concentration and flow, and we multiply that relationship by the previous information, the flows in the rivers, then we can calculate an estimate of how much phosphorus the rivers are annually delivering to the lake. And this is the result of that calculation. This is from a manuscript by Greg McCulloch and myself and some others. And the reason the right side of the figure is in stronger color is that those are the 40 years where we have actual data on the concentrations. We've used the same relationship on the historic flows earlier than that. But when we look at the phosphorus loading to the system, what really stands out importantly is that the Red River delivers far more phosphorus to the lake than the other two rivers. And this is in spite of the fact that the Red River only carries about 15% of the water that's going into the lake. But depending when you look, it's on the order of 60 to 80 plus % of the phosphorus that goes into the lake. So really, I think this points out to us that our focus in addressing the phosphorus problem going to Lake Winnipeg must be on the Red River and its basin. Now, the next question we'd want to ask after seeing this is, why are we getting, first of all, so much more flow from the Red River, and why is that flow then delivering so much more phosphorus? Well, here I've put together the precipitation records from Winnipeg and from an average from the state of North Dakota, Winnipeg in blue and North Dakota in green, and those apply to the axis on the left. Winnipeg averages just above 500 millimeters per year. The state of North Dakota averages about 440 millimeters per year, and those are what represented by those lines across. And then below that, I've plotted now in the same units the water flow, the flow of the Red River. And in order to create that graph, I simply divided the total flow data that I showed before by the total area of the Red River Basin. So what we can see is, first off, is that though we get precipitation of about 450 to 500 millimeters on average, we only get 10 to 50 millimeters of runoff. So in the long term, only about 5% of the water that falls on the Red River Basin runs out of it in the Red River. And that's because generally, especially farther to the west, we have a very dry system here and it's very flat. Runoff is not quick. The other thing that we notice, though, is that the changes in precipitation, if you look at the long record of precipitation, are not really that dramatic. What one can notice is that in the last 15 years, we have had a period where the precipitation has been consistently well above the average. And there are few periods prior to that where we have precipitation consistently above the average. But it's nothing compared to the dramatic changes in the river itself. There is another feature in the basin that impacts this, and that is over the last 50 to 100 years, there has been a huge amount of effort putting drainage into the system. And this is just a diagram of the drainage system in the LaSalle River, just southwest of Winnipeg. And the striking feature of this is there is very little storage. So this system is designed to get water off the fields as fast as possible, and as a result of there being virtually no storage, especially in the lower part of the basin, it delivers that water that comes off the field very rapidly to the rivers. And that means we're very efficiently removing the water, and we're causing some potential problems. So, in conclusion, I think I can simplify this by saying farmers want excess water off their land quickly, both during dry and wet periods, because they can't work when there's water standing on the land. In wet periods, this results in serious downstream flooding because we're delivering this water so rapidly to the rivers, and we've certainly seen that in the last couple of years. And because higher flows deliver much higher loads of phosphorus, this results in excessive nutrient loads to Lake Winnipeg. In dry periods, this still can result in downstream flooding if we get very heavy rainfalls because the water is delivered so rapidly, but it also results in the loss of water from the land, and in dry periods, of course, that is a risk to farming. So we also have noticed that that storage of water in the basin is very limited, and I think that storage is the sensible option here. As an example, in order to store 25 millimeters of precipitation in a pond with 500 millimeters of storage, so a pond that can go up and down half a meter, one would have to commit 5% of the land. If we turned 5% of the land into ponds that could go up and down half a meter, we could store 25 millimeters of precipitation. And 25 millimeters of precipitation is equal to the average amount that runs off the basin, or equal, in a sense, to the excess amount that is presently running off the basin. So I think what we really need to do is take this drainage-only system that has been developed over the last 50 to 100 years and convert that to a system of drainage and storage. And that's going to be a long process as the process to create the drainage system was, but I think it's the only sensible solution in the basin. Thank you.